In today's video, we'll learn about heat engines. So what is a heat engine and how does it work? A heat engine takes an energy by heat and partially converts it to other forms such as electrical and mechanical energy. Heat engines work in a cyclic process and the internal energy remains constant. So we get the equation that our net energy absorbed is equal to the work done by the engine, and that we can calculate the net energy absorbed by taking the absolute value of our energy taken from the hot reservoir minus the absolute value of the energy taken from our cold reservoir. To determine how efficient our heat engine is, we can look at the engine's thermal efficiency, which is the work done by the engine divided by the energy absorbed during one cycle. So in our equation below, E is our symbol used for efficiency, which is equivalent to 1 minus our absolute value of Q cold divided by the absolute value of Q hot will give us our thermal efficiency of our engine. And so if we were to get efficiency of 1, which is an efficiency of 100%, the only way that this would be possible is if the energy from the cold reservoir is not lost to the environment, which we know is impossible. So if we look to our right, we have an example of a heat engine where we see that the energy from the hot reservoir is being absorbed by the engine, which is transformed into electrical or mechanical work, and the excess energy is then given off into the cold reservoir. Now, refrigerators are like heat engines, but work in the reverse direction. Energy is extracted from the cold reservoir as work is done on the system, and the energy is transferred to the hot reservoir. So, our energy from our hot reservoir is equal to the energy from our cold reservoir plus the work done by the engine. Another type of engine we have are heat pumps, which can be switched between a cooling mode and a heating mode, and the performance can be measured by measuring the coefficient of performance. And so, in order to measure the coefficient of performance while the heat pump is in its cooling mode, we would take the absolute value of the energy from the cold reservoir divided by the work done by the engine. And in the heating mode, we would take the absolute value of the energy used in the hot reservoir divided by the work done by the engine. So we looked at a heat engine in the last slide. Now we see we're given a refrigerator where the energy is absorbed from the cold reservoir plus the addition of work being done on the refrigerator will produce electrical or mechanical energy, where the excess energy will be then transferred to our hot reservoir. So we know that the efficiency of an engine cannot be equal to or greater than 100%, which then brings us to our second law of thermodynamics, which states that no heat engine operating in a cycle can absorb energy from a reservoir and use it entirely for the performance of an equal amount of work, which basically states that no engine can have an efficiency above 1, and that some of the energy taken from the reservoir must be lost to the environment. However, the closest engine we've gotten to having a thermal efficiency close to 100% or equal to 1 is the Carnot engine, which involves a heat engine is operating in an ideal reversible cycle between two energy reservoirs, and that the efficiency of this engine depends on the temperatures of the reservoirs. So we can calculate thermal efficiency of a Carnot engine by the equation that states that is equal to 1 minus our cold temperature divided by our hot temperature, where our temperature is measured in kelvins. And at the bottom of our screen, to the right, we see we have the process of a Carnot engine, which involves isothermal, adiabatic expansion, isothermal, and then adiabatic compression. And through this process, we're able to create a Carnot engine. So we're given an example that states that a power plant has been proposed that would make use of the temperature gradient in the ocean. The system is to operate between 20 degrees Celsius, which is the temperature of surface water, and 5 degrees Celsius, which is the temperature of water at a depth of about 1 kilometer. In part A, we're asked, what is the efficiency of such a system? So in part A, we're just asked to calculate the efficiency. So we know efficiency can be calculated by taking 1 minus our cold temperature divided by our hot temperature. And since we're giving a temperature gradient, we see that our cold temperature would be equivalent to 5 degrees Celsius. And since our efficiency has to be measured in the Kelvin scale, we can convert our Celsius into Kelvin, which will give us a value of 278 degrees Kelvin. And then our hot temperature would be 20 degrees Celsius, and once it was converted into our Kelvin scale, it had a value of 293 degrees Kelvin. So now we can use our efficiency equation, which states that 1 minus our cold temperature of 278 degrees Kelvin divided by our hot temperature of 293 degrees Kelvin will give us an efficiency of the engine, which is approximately 0.0512, or if we were to convert it into a percentage, if we times it by 100, we see that a percentage of our thermal efficiency would be approximately 5.12% efficient. In part B, we're asked if the useful power output of the plant is 75 megawatts, how much energy is absorbed per hour? So in part B, we're given that the power of the power plant is 75 megawatts, and we're asked to solve for the amount of energy that is absorbed. So this would be the amount of energy that is absorbed from our hot reservoir. If we are given the equation that our efficiency is equal to the work performed by our engine divided by our absolute value of our energy absorbed from the hot reservoir, we can rearrange this equation to solve for our energy from our hot reservoir, which will give us the equation that our hot reservoir energy is equal to the work done by our engine divided by our efficiency. And we know that power is equal to work over a change in time. So from the equation we see that work is equal to power times our change in time. So we can plug this in for our work done by the engine, which would give us a final equation that states that our energy absorbed from the heat reservoir is equal to our power output multiplied by our change in time divided by our efficiency. So now we can plug in our values to solve for our QH. So we know that our power is 75 megawatts, and if we convert that to watts, we would have 75.0 times 10 to the 6 watts, or joules over seconds, multiplied by our time of 1 hour in seconds, which we know that 1 hour has 3,600 seconds, divided by our efficiency of our engine, which was equal to 0.0512. And when we do so, we see that the energy that is absorbed from the hot reservoir is equal to 5.27 times 10 to the 12th joules of energy.